Hello physics class, coming back to you again with another physics video. Hopefully these are educational, and if you're feeling up to it, like, comment, and subscribe. Just kidding, I really don't care. I don't really use YouTube much. Anyways, we have a circuit here. We're given these capacitances, and we're given this charge too on this capacitor. So this problem first asks us, what is the equivalent capacitance? And part B is, what is the charge on C1, capacitor 1? And part C is, what is the total energy stored in the capacitors? So I'm just going to do everything I can find in this problem. So that way, we're looking for everything we could quite possibly be asked for a capacitor problem. And this is similar to something you could see on an exam of this difficulty. So I'm going to start by drawing my table. So I have C1, C2, C3, and C4. Alright, and setting up my table, we know that Q equals C delta V, so C, delta V, and Q. And now, I like to look at my potential combinations before I do anything so I can figure out how I'm going to do this problem. So looking at the circuit, we know 4 and 3 are in parallel, so I'm going to end up combining those, C3, 4. And then I have 3, 4 now. That combination is in parallel with capacitor 2. So I'll have capacitor 2, 3, 4. And then I'll have 2, 3, 4 combined with 1 in series. And now filling in my knowns into my table, I know capacitor 1 is a charge of 4, or a capacitance of 4, excuse me. Capacitor 2 has a capacitance of 2, capacitor 3 has a capacitance of 4, capacitor 4 has a capacitance of 6. And the charge on capacitor 2 is 12 microcoulombs. So I'm going to start this by finding all of my capacitances for these three combinations. So C3 and C4 are in parallel, which means you just add the capacitances. So C3, 4 is just 6 plus 4 is 10 microfarads. So this capacitance is 10. And then now I'm looking, I have 3, 4 in parallel with 2. I like to draw these big red circles just so I know what I've already included. And that is in parallel, so again we add the capacitances. So we have C3, 4 plus C2, 10 plus 2. We get C2, 3, 4 equals 12 microfarads. And lastly, now we have C2, 3, 4 in series with C1. So we just draw an even bigger circle. And these are in series, so we do 1 over 12 plus 1 over 4, negative first. Or you can also do the thing I taught you guys, 12 times 4 over 12 plus 4. And this will give you 3 microfarads, which is your equivalent capacitance of the circuit. And C234 is 12. And I don't know why I put units there. You don't have to put units in here. They're usually going to be nice so that you don't have to worry about conversions or anything. But do be aware that they are there. So now I'm just looking at this table. I'm going to start filling things out. I know I can find this delta V by taking Q divided by C and getting 6. And I know C2 is in parallel with C3 and C4, so they will all have the same voltage drop. Then I can find my charges by multiplying. And now what do I know? I know that 2 and 3 and 4 are in parallel. So now I can start looking at these equivalent capacitors. C3, 4's combination in parallel, so the voltage is the same, 6. 2, 3, 4 again in parallel, 6. And I can find these charges, 60, 72. Alright, so I have everything except information about capacitor 1. I know that capacitor 1 is in series with capacitor 2, 3, 4. In series, the charges are the same. So I get that the charge on capacitor 1 is 72 microcoulombs. And that's part B as well. But I'm going to finish this table anyways. 72 divided by 4 is 18. And now looking at my equivalent, C1234 is a combination of 1 and 234 in series. It has the same charge. And it has a voltage of 72 divided by 3 is 24. Right. Well, now I have my whole table. I can just find my my total energy stored in my capacitors. I now have I have a circuit like this. I know this capacitance is 3 microfarads, has a charge of 72 microcoulombs, and my voltage drop is 24 volts because that is the voltage drop across my capacitor. So I can calculate energy in 3 different ways. So U is 1/2 Q delta V. So 1/2 times our charge, which is 72, times our delta V is 24. This will give you 864 microjoules. Again, I could also use other equations. U equals Q squared over 2C. Q squared, Q is 72. So 72 squared over 2 times 3. And I'm still going to get the same answer, 864. And I could use the other equation, 1/2 C delta V squared is just 1/2 times 3 times 24 squared. Again, still going to get the same value no matter which one I use. All right. So moving on to the second open-ended question, if this ever lets me clear. All right. Now we're looking, we have, instead of capacitors, we have resistors. This is a pretty simple circuit. So we have R1, R4 here, R2, R3, and this is 8 ohms. R2 is 10 ohms. R3 is 10 ohms. R4 is 5 ohms. So what is the equivalent resistance of the circuit? Well, combining these two in series, we'll get 1/10 plus 1/10 inverse. That just gives us 5. Now, this combination is in parallel with this. Or sorry, I made a mistake here. These are in series, R2 and R3. So you just add them. So 10 plus 10 equals 20. Now R23 is in parallel with R4. So we have 1/5 plus 1/20 inverse. That is going to simplify to 4 ohms. And then lastly, we have 234 in series now with R1. So we have 4 plus R1 is 8, just gives us 12 ohms. All right. And now we want to rank the resistors in terms of the voltage drop across each resistor. So you can do this multiple different ways. I'm going to show first the analytical way of just looking at the circuit, and then I will show some of the calculations. So looking at this, we know 2 and 3. We have 2 and 3, right? These are the same resistance, and they're in series, so they have the same current going through them. So they're equal, the voltage drops. So delta V2 equals delta V3. Now when we combine these, remember when we combine resistors in series, their voltages add. And now we'll have 2, 3. So let me redraw this just to avoid confusion. We have 1, 4, and 2, 3. 2, 3 is in parallel with 4. So the voltage drop across 4 equals the voltage drop across 2, 3. Remember we said with the voltage drop across 2, 3, it's just equal to the voltage drop across 2 plus the voltage drop across 3. And that equals, in this case, the voltage drop across resistor 4. We know since V2 and plus V3 equals V4, V4 has to be greater than V2, and V4 has to be greater than V3. So right now we know that delta V4 is greater than delta V. Let me fix that. Delta V2 is greater than delta V. Oh wait, these are equal to delta V3. So what about delta V1 now? Well, if we're combining these resistors now, we know that these have the same voltage drop across them. So what does that mean for our circuit? We know that delta V1 equals, delta V1 plus, because this V1 is in series with this combination. So delta V1 plus delta V234 equals the EMF. So now we want to look at these and say which one has a higher resistance. R1 has a resistance of 8 ohms. R234 has a resistance of 4 ohms. We know that V equals IR. These are in series, so they have the same current going through them. But the V234 has a smaller resistance. Since resistance is directly proportional to voltage, we get that V1 is greater than V234. And we said V234 is the combination of all of these resistors. So V1 has to be the greatest voltage drop. So here's our voltage drops. And that is our ranking, as the problem asks. And you could do it the other way. You could set up your table, find the voltage drop across every resistor, and then you will get the same result. I will say that for you guys to do. And then if you guys are still stuck on it, I will go over it on office hours tomorrow on Tuesday. All right. Part C now. Part C. It's saying now treat the battery as a real one with an open circuit voltage of 12 volts. And this is our ideal. And this internal resistance is 4 ohms. We want to know the voltage drop across the terminals when this load resistance is here. Well, we got our load resistance to be 12 ohms, right? We look over here, 12 ohms. We want to find this delta VL. Delta VL is the voltage drop across our resistor. And why is that the case? Because this internal resistance is technically part of the battery. So this is our sort of new battery. Kind of looks like a potato, so I apologize. Anyways, if we're just analyzing the circuit, we know our current through this whole thing. So getting rid of that red circle. We know our equivalent resistance is Ri plus RL because they're in series. We know V equals IR, so I equals V over R. Our voltage drop is just E across the equivalent resistance over our equivalent resistance, Ri plus RL. And that equals I. To get delta VL, the voltage drop across our load resistance, delta VL is just I times RL, or our current is just E over R internal plus R load times R load resistance. And this is an important equation to know, FYI. So plugging in our values now that we just derived this, we're trying to find delta VL, so just plug in our values. 12 times our load resistance of 12 over 12 plus 4 is 16 will give you 9 volts. All right. So moving on to the last problem, I'm going to exclude the bonus because it will not be on the test. I'm 99% positive, but if you're curious about that, I could surely go over it at some point. So now drawing my last problem. This is problem 3 on the challenge problems for anyone keeping track. I'm going to draw this in blue because it's positive. And then this one in red because it's negative. Just helps you visualize it more. Alright, we have a charge of mass m with a speed v naught. When this charge reaches point 2, its speed is 2v naught. We want to know the voltage at point 2, which we'll essentially find, but we want to know the charge, which is part B. Part B, we need part A to find part B, so I'm just going to simply solve part B. So what is the charge? Let's start with our basic relationship for conservation of energy. Delta K, change in kinetic energy, equals our negative change in potential, which is equal potential delta U is equal to negative Q delta V. So solving this, we get Q equals negative delta K over delta V. Let's find this delta V. So just at the side, delta V, it's starting at 1 going to 2, so it's going from 1 to 2. Its final is 2, its initial is 1. Well, V2, if we're looking at 2, these are our two charges that create a voltage. So remember our voltage is just KQ over R. Well, we have this positive charge, so we have 6kW, 6 times W times K, over our distance. We have L plus L is 2L. And then we have this negative charge, so minus 6kW over distance L, 3L. And then we have minus V1. V1 is here. Our positive charge, we have 6kW over this distance is L. And then minus this negative charge, because it's negative, that's why there's a minus sign. 6kW over 1, 2, 2L. And then simplifying this, let's see, we have 3. I'm going to pull out the kW over L. We have 3 minus 2 is 1. Minus 6 minus 3 is 3. So we get negative 2 kW over L equals delta V. Awesome. So solving for our charge. Charge equals our negative delta K, which is negative KF minus K naught over delta V, which we got negative 2 kW over L. Canceling out these negative signs, of course. Kf is our final kinetic energy, which is just 1/2 times our mass, times our final velocity squared, which is our final velocity is 2v naught, minus our initial kinetic energy, 1/2 m. Our initial velocity is v naught, v naught squared over 2kW over L. And then doing some algebra here, let's see, we get 1/2 m. This is 4v naught squared minus v naught squared. So 3 v naught squared divided by 2kW over L, and the L will pop up. So this simplifies to 3m v naught squared L over 4kW. And that is our charge. It asked for voltage at point 2 as well. That's just this expression, which would be 3 kW over L minus 2 kW over L would just be kW over L equals V2. Alright, so that concludes the exam review. I would be doing office hours on Tuesday if you have any questions about this, and I'm also bringing my challenge problems. So thank you for watching, and have a good day.